Okay. Whoop. All right. So I'm making this video because I stumbled upon the solution for 2.1.3 when I was looking for hints online. And I didn't really understand it at first. Um, and so I had kind of done some mapping to help my own understanding. And I think I understand the solution now, but I'm not 100% on how to write a formal proof of it. And so I'm just going to kind of talk about the solution a little bit instead. Um, so the solution is to show that there are infinitely many left inverses for our function s of n, is to let L sub k of n equal this piecewise function, which says that the function is n minus 1 when n doesn't equal 1, and that it's equal to k when n does equal 1. And k is an element of the set of natural numbers. Excuse me. Okay. So here we have the domain and codomain of L. So we're going to start by taking a look at that. And in both cases, it should be the set of natural numbers. And so what we can see is that 1 in the domain maps to, 2 in the domain maps to 1 in the codomain, because it's not equal to 1, and we're just subtracting 1. 3 would map to 2. I didn't show it, but 4 would map to 3. 5 would map to 4, so on and so forth. However, 1 maps to k in the codomain, because that's the way we've defined it. Okay, so let's take a look at what that looks like in some different versions of the function in this family of functions. So let's start with L1. So on this one, 2 maps to 1, 3 maps to 2, and 1 maps to 1, because we've defined k to equal 1 for this function. With L2, 2 maps to 1, 3 maps to 2, and 1 maps to 2. For L3, I'm going to add 1 to the domain. So 2 maps to 1, 3 maps to 2, 1 maps to 3, and 4 maps to 3. Why didn't I show that? I meant to show right here that 4 maps to 3 for this one. Okay, so now let's do some mapping for L sub 1 of S of n. So here I have that the domain of S of n is the set of natural numbers. I'm going to show how that maps onto the codomain of S of n, and then show that the range of L sub 1 of S of n is the set of natural numbers. For S sub n, 1 maps to 2, and then using L sub 1, 2 will map to 1. 2 will map to 3, which will then map back to 2. 3 will map to 4, which will then map back to 3. So you can kind of see that, as we go through this progression, we're going to map to every single number in n with our range of L sub 1 of S of n. And so L sub 1 should work as a left inverse for S of n. We're going to see basically the exact same thing for L sub 2, right? 1, 2, and 3 in the domain of S of n, map to 2, 3, and 4 in the codomain of S of n, and those will map back to 1, 2, and 3 in the range of L2 S of n. And this will be true. I think to actually prove this, you would have to do induction. Maybe I'll try to do that here. Okay. So then L sub 3 of S of n. Okay, so again, 1, 2, and 3 map to 2, 3, and 4, which map back to 1, 2, and 3. So I think this is, roughly showing that L sub 3 works as a left inverse for S sub n in n. And I think we can generalize that L sub k will work. I think I would need, I've kind of shown my initial steps. I would need to show that I would this is where I would, need to do my proof by induction to actually prove it and actually show that the k plus 1 step works. Okay. So now I kind of want to show why L sub k doesn't work as a right inverse. So what I can show here is that in L1, 1 maps to 1, 2 would also map to 1, 3 would map to 2. If I were to continue showing this, 4 would map to 3, 5 would map to 4, so on and so forth. And then 1 maps to 2, and 2 maps to 3. So what ends up happening is that the range of S of L sub 1 of n is not onto the set of natural numbers because nothing maps to 1. And I think that's the problem, that's why this isn't a true right inverse, is if I put 1 in for n, I don't get 1 as an output. I think I can say the same thing about L2, right? 1 maps to 2, 2 maps to 1, 3 maps to 2, and then 1 and 2 in the codomain of L sub 2 of n are going to map to 2 and 3 in the range of S of L2 of n. But again, I think I can say that that range is not onto the set of natural numbers. S of L2 of 1 does not map to 1, so this isn't a true inverse. And we can say a similar sort of thing for S of L3 of n. So 1 would map to 3, 2 would map to 1, 3 would map to 2, 4 would map to 3. 1 map in the codomain of L sub 3 of n. When we apply the S function, 1 would map to 2, 2 would map to 3, 3 would map to 4. But again, in my S of L sub 3 of n, S of L sub 3 of 1 does not map to 1. And so, again, not a true inverse. And then we can show this more generally with k. I don't know if this is approaching a proof by induction to show that this left inverse doesn't work as a right inverse, right? So I can show that 1 maps to k, 2 maps to 1, 3 maps to 2, right? If I had written 4, 4 would map to 3. K maps to k minus 1. K plus 1 is going to map to k. And then 1 would map to 2, 2 would map to 3. K minus 1 would map to k, and k would map to k plus 1. And so again, we can show that for S of L sub k of 1 does not map to 1. So it does not map onto n. So hopefully this works as kind of an explanation for why S has infinitely many left inverses but no right inverses.